Hi, we're we're back. Collingwood High School, Advanced Topics in Mathematics, Spring 2020, Part 2 of Finding Prime Numbers. So we left off at the end of the last lecture with the idea that we're going to try to develop an algorithm that is going to attempt to quickly locate prime numbers for us, and that we need a little bit more number theory in order to be able to understand how the algorithm works. So I'm going to do that number theory in this lecture here. So what we're going to talk about is a few things. We're going to talk about what is a quadratic residue. And we're going to talk about some special symbols that we use in this context, the Legendre and the Jacobi symbols. And then we will also talk about the law of quadratic reciprocity. So this, in particular, the law of quadratic reciprocity is a major result in number theory, and it was conjectured originally by Euler and Legendre, and it was proved by Gauss. So he was I think he was about age 21 when he did that, for the record. So we're going to introduce this thing. I'm going to go through some examples. This is something that likely you have not seen before, so you want to go slowly enough, making sure that you have understanding of each part as I go along. And then also we'll be having a Zoom lecture. You want to make note of any things that are not clear, any questions that you might have that we can discuss when we have our Zoom lecture next week. Okay, so let us first introduce the term quadratic residue. Okay, so I'm going to have here P and odd prime. So that basically is only excluding 2. So we're going to have P and odd prime. And I'm going to have A, an integer. And I'm going to have, well, I don't actually need anything else. I'm going to tell you that A is called a quadratic residue, mod P, if A is not congruent to 0 mod P. And, so okay, first A is not congruent to 0. So A is not divisible by P. And y squared is congruent to A mod P, has a solution for y in ZP. Okay, so let's just read through that again. A is a quadratic residue if it's not equal to 0 mod P, and there is some other number y such that when you square y, it is congruent to A mod P. Okay, so let me think about a way of potentially remembering this definition. One is to take a look at the word. So A is a quadratic residue. I might be thinking of this residue, much like if you spill something on the table, like a cup of coffee, and then it dries, and then there's a leftover stain on the table. We call that a residue. So we call this perhaps like a leftover. Okay, a leftover. So I'm thinking if I take some number y and I square it. Okay, now I'm noticing I'm squaring it. Then power of 2. Okay, quadratic equation is x squared, possibly plus ax plus b. Sorry, yeah, like so. Let me just let me say that again. Quadratic equation looking like this: ax squared plus bx plus c. That's a general quadratic polynomial, and if it was a quadratic equation, it would look like that. And the highest power of x is 2. That's why we call it quadratic. And so this is the same thing. I could identify by this word quadratic that I'm looking at. I'm saying, okay, if I take some number y, and y is in ZP, then I square it, and then I take mod P, so I remove all the factors of P that I can, and it turns out that A is left over. A is left over, then A is called a quadratic residue. So it's sort of what is left over if I square some number and remove all of the multiples of P. Okay. We're going to do an example here. Just before that, we'll just state what is a non-residue, because now that we know what is a residue, we can say what is a non-residue. So A we would call a non-residue. So A is called a quadratic non-residue, mod P. If A is not congruent to 0, that's the smaller problem. So it's just if it's not 0, and A is not a quadratic residue. All right, let's take an example. Let's take a look if P was equal to 11. So we're going to consider the integers mod P, which we're going to designate in that manner there, Z sub 11. So P is 11. And so we have the numbers from 0 to 10 in the in this set here. So we're looking here at the numbers 0, 10, like that. Those are the numbers, one of the equivalence classes, mod 11. We're not going to be considering 0. So let us take a look, because we have this condition here. So let's take a look at what happens when we square all of the numbers in Z11. So I'm going to just take all of the numbers in Z11 excepting 0 and look at what happens when I square them. What number do I get? So I'm going to take 1, I'm going to square it, and I will get 1. And I do mod 11, but I don't have to do anything here. Then I'm going to do the next one. I'm going to square 2, and I'm going to get 4. And then I'm going to square 3, and I'm going to get 9. I'm going to square 4, and 4 squared is 16. 16 mod 11 is 5. So 4 squared is 5. And then I will square 5. 5 squared is 25. 25 mod 11 is, you subtract 22. 25 minus 22, you get 3. Okay, 6 squared, 36. Mod 11, 3. 7 squared, 49. Mod 11 is 5. 8 squared, mod 11 is 9. 9 squared, mod 11 is 4, and 10 squared mod 11 is 1. Okay. So I took every possible number excepting 0 in Z11 and I squared it, and then I see what the remainder is, mod 11. Right, so what does it equal mod 11? So let me just box those numbers now that I'm interested in. These are the numbers I'm interested in. Okay, let's just take a look at what numbers I got. Okay, so I got 1. I'm just going to make a list of the numbers I got. 1. I got that one here. When I did that, I got it here. What other numbers did I get? Let me look for the next smallest one. I got 3. I got 3 right here, right here. And what other number did I get? I got 4. Got 4 right here. That's all. And I got 5. I got that here, 5. And I got 5 here as well. Oh, I did get another 4. So I've taken care of that one. 4. And I got 4. And then what other numbers do I have? 9. That's it. Those are the numbers that I got. 1, 3, 4, 5, and 9. Okay, you notice that of all the numbers in Z11, 1 through 10, I didn't get them all. Like, it's not the case that all of them showed up. Like, I'm missing 2, I'm missing 6, I'm missing 7, I'm missing 8, and I'm missing 10. So some numbers are missing. And so what I'm now saying here is that the quadratic residues the quadratic residues mod 11 are 1, 3, 4, 5, and 9. Okay. That means if I make an equation that looks like this, y squared equals 4 mod 11, I will be able to find a solution. I mean, in this case, I know that because I've listed them all out. But if I know that this thing here is a quadratic residue, then I know that I can solve this quadratic relationship here, y squared equals 4. And in fact, what are the solutions here? I mean, we can just look above and see what the solutions are. That is going to be here. Y is equal to 2. Because 2 squared is equal to 4 mod 11. And do we have another one? Yes, we do. It is right here. And that is y is equal to 9, because 9 squared is also equal to 4. I'm going to point right now to the fact that 2 is equal to minus 9 mod 11. 2 is equal to minus 9 mod 11. Okay, let's look at another equation. I could say to you, what are the solutions? What are the solutions to this equation? Y squared is equal to 9 mod 11. Okay, so you could look above and say, okay, if for that to happen, y is going to have to be equal to another color here. I'm going to have to look above. Y is equal to, okay, I'm wondering what number do I square? If I square some number, what number is it such that I will get 9 mod 11? So I look up here, I see that 3 will work. 3 squared is 9. And then I see also what else will work? 5. So y is equal to 5. So we have that, sorry, what am I saying? Hang on, sorry, I retreat from that statement. No, I did this wrong. I just noticed they're not negatives of one another, so I realized I had made a mistake. We're looking for the ones that are equal to 9, not the ones that are equal to 3. Okay, for what numbers is y squared equal to 9? 3, and then where, this is not correct, where is it also equal to 9? It's right here. Y is equal to 8. Okay, because 8 squared is also 9. And I also am going to notice here, just in passing, that 3 is equal to minus 8 mod 11. Okay. Okay, so the quadratic residues are the ones that you can find if you go and square every number. They also can be looked at in this other manner. Is it if I was to try to be solving a quadratic modular equation, I would be able to solve the equation for this number a being in this set here. Okay, so those are the quadratic residues. Let's then also just write out what the quadratic non-residues are. Quadratic non-residue mod 11 are the ones that are not in this list here. I mean, these are the ones that we found, and these are the ones that are not in the list. That is going to be here 2, 6, 7, 8, and 10. So those are quadratic non-residues mod 11. Okay, that means if I wrote an equation like this, y squared is equal to 6 mod 11, find y, it is not going to be happening. You are not going to be able to find a y in Z11 such that y squared is equal to 6. That won't happen. Okay, so there is no solution here. Okay, so that is why it's called a non-residue. 6 is never a leftover when you square something and then reduce mod 11. Okay, so this is not possible. There is no y in Z11 such that y squared is equal to 6 mod 11. So we've basically divided the numbers in Z11 into two categories. They're either a quadratic residue or they are a quadratic non-residue. That's what that word means. Okay, so then we can kind of, we made a sort of an exhaustive study in this case here. Then we could come here and we could, in sense, ask a kind of question. So these are, for example, I could ask, is 1 a quadratic residue mod, let's try to make that a little bit neater, is 1 a quadratic residue mod 13. So for example, in Z13. Or I could ask, is 10 a quadratic residue mod 13? So these are the kind of questions we could ask. I mean, clearly coming into our final exam, this is going to be our final topic. We'll be asking some basic questions about quadratic residue. Okay, so we can see, first of all, we can identify for a small prime, we can fairly easily, by brute force, identify all of the quadratic residue and all of the quadratic non-residue. These are sort of questions you can ask. Okay, so I'm going to make a couple of statements here that I will prove. Let us, we're considering here P and odd prime. Keep saying this, but 2 is just a bad number in this context. We're never going to be having 2. 2 is not allowed. It's even, and it just throws out everything. So we're always considering basically all the primes except 2. So P and odd prime. Okay, and a statement here. If A is a quadratic residue then there exists Y in the non-zero elements of ZP such that Y squared is congruent to A mod P. That's what we just saw above in our example. Further, minus Y squared is equal to, is congruent to A mod P, and Y is not congruent to minus Y mod P. Okay, hang on a second. I might, but that statement is bothering me slightly here. Hang on, let me just go through this here. Consider x squared minus a congruent to 0 mod p. Okay, that means, of course, this is just another way of writing A is a quadratic residue, QR, implying that y squared is equal to A. I mean, I'll just move the A to the other side. Okay, so I'm going to factor this thing here. It's going to be x minus something times x plus something, and that will be congruent to 0 mod p. Okay, what does that mean? That means that p divides x minus y, or p divides x plus y. Okay, I mean, p is prime, so if p divides the whole number, then p has to divide one of the two factors. Okay, so that means this statement here, p divides x minus y, or p divides x plus y, means that x is equal to plus or minus y mod p. Okay, so that means for this equation right here, x squared minus y congruent to 0 mod p, there are two solutions. Therefore, x squared minus a congruent to 0 mod P has two solutions, and they are negatives of one another. I'm just going to okay, and then we saw that, in fact. So let's just scroll back up here. We saw that if we found a solution, if A was a quadratic residue, we could find a solution to y squared equals A, which is the same as here, which is the same as y squared minus 4, congruent to 0 mod 11. Okay, so we found if this 4 here is a quadratic residue, we could find a solution to this equation. We found, in fact, two solutions, and then we found that they were the negative of one another. And we have just showed that is, in fact, always the case. So if A is a quadratic residue, then there exists some y such that y squared is equal to A. And further, it is also true that minus y squared is also congruent to A. Okay, and then we just we went through here by factoring and using a divisibility argument to show that that indeed is the case. Okay, so what we're going to want to do now is determine if A is a quadratic residue. So that's our problem without say, for example, squaring every single number and looking to see whether we can find it. So for example, when I posed the question, I could pose the question looking at this list of numbers. If I look at this list of numbers here, I could pose the question, is I don't know, let me just pick one, is 4 a quadratic residue? And then I would be looking through here. As soon as I found the 4, I would then say yes. And I could say, is 7 a quadratic residue? And then I would look through at all these numbers like that. And I would go along and I wouldn't find 7, and then I would say, no, 7 is not a quadratic residue. Clearly this is a slow way of doing it. Not only that, I have to square every single number here and look at what the result is. So what we're wanting to do now is answer the question, is some number A a quadratic residue mod P? How do I do that? Okay, that's what I'm going to do next. So I'm trying to make clear what the question is. We are attempting to determine if A is a quadratic residue. So here's our problem. Given an odd prime, and an integer A, we ask the question. There's that we're given this, okay? Then we ask the question: is A quadratic residue? This is the number A. Is A, I'll put it like that in the LaTeX model, is A quadratic residue mod P? That's what I'm asking. Okay, and we're going to get at the answer to this problem without doing the brute force approach. The brute force approach works though, and indeed it may be the fact that on our coming final exam that I would ask this kind of question, and there's nothing wrong if the modulus, if the P is small, to just quickly square every number, list them all out, and then you can say exactly which numbers are quadratic residue and which ones are not. But clearly when P gets to be larger, you want a better method, and the method that we're going to use is based upon this theorem. Okay, here's the theorem. The theorem is called Euler's criterion. Okay, let P be an odd prime. Okay, P is an odd prime. Then A is a quadratic residue mod p if and only if a to the p minus 1 over 2 is congruent to 1 mod p. Okay, I want to draw your attention to the if and only if. When a theorem is stated that way, and we've done this before, but just to remind you, when a theorem is stated this way, this came up on the midterm, you must prove it both ways. So what you do is, in this case, you would say, suppose A is a quadratic residue, and then you would show that this then holds. And then you go the opposite way, you suppose that this holds, and then you show that A is a quadratic residue. So when you see the if and only if type of proof, you must prove it in both directions. It's a necessary and sufficient condition. So we're going to do that here. We're going to prove this theorem, Euler's criterion. Okay, here is the proof. Okay, so we're going to go, I guess what's where the theorem is stated, we're going to go in the forward direction first. So I am going to suppose A is congruent to y squared mod p, where y is in ZP. Okay, I'm going to I'm going to suppose that. Now I'm going to show that this condition here holds based on the supposition that I have A being a quadratic residue. So here y is in ZP. Okay, and it's not 0. Okay, first thing to notice is P is prime. P is prime. So we have that A to the P minus 1 is congruent to 1 mod P for any A not 0 mod P. Okay, where does that come from? This one here, we've seen this before. This is Fermat's little theorem. So we can use that here. I mean, A and P are co-prime, but because P is prime. All right, so now I'm going to take A to the P minus 1 over 2, and that is going to be congruent to, well, what is A? A is y squared. Because I assumed that A is a quadratic residue, so A is y squared mod P. So I'm replacing A with y squared, and then I have that same exponent there, P minus 1 over 2 mod P. And then that is congruent to y to the P minus 1 mod P. And then what is that equal to? That is congruent to 1 mod P. Why is that? Okay, well, it's because P is prime, and the order of y is going to be P minus 1. So y to the P minus 1 is going to be y for all y in ZP. Okay, so this, what you're wanting to recall here is the order of an element in a group. Okay. Okay, so we have now, in fact, the one direction. We have started with the fact that we started with the assumption that A is a quadratic residue, and then we have showed down here that that means if A is a quadratic residue, then it is true that A to the P minus 1 divided by 2 is congruent to 1 mod P. So now we've done the proof in one direction. Now we're going to go in the other direction. So we are going to conversely suppose, we're going to now suppose that A to the P minus 1 over 2 is congruent to 1 mod P. We're going to suppose that. And then we're going to try to show that this means that A is a quadratic residue. Okay. All right. So let's start going. Let B be a primitive element mod P. Then A is congruent to B to the I mod P for I in some positive integer. Z plus, that's a positive integer. Okay, so every element A is B to the something, where B is some primitive element. So we've seen this before too. Okay, so that means that A to the P minus 1 over 2 is congruent to B to the I P minus 1 over 2 mod P. Okay, and B has order P minus 1, it's primitive. Okay, and thus we have the fact that P minus 1 divides I P minus 1 over 2. Okay, I is, we have that P minus 1 divides I times P minus 1 over 2. Let's think about that, what that means. That means that I has to be even, because we've got this 2 in the denominator, and this thing is going to divide into here with a quotient of I divided by 2, and we know that this has to be an integer, so that means that I has to be even. Okay, otherwise it won't divide in and without without a remainder. Okay, so I is even, and therefore the square roots of A are plus or minus B to the I over 2 mod P. Okay, we had that A was B to the I, and now we are positive that I is even, so therefore we can take the square root by representing the square root of A as, well, here, like this, A to the 1/2. The square root of A then is congruent to B to the I over 2. And so the square root of A exists because we have assured ourselves that this thing is even. Okay, what does that mean? Well, that means that A is a quadratic residue. And we are done. Okay, so now we're in the situation that if we want to know, I'll wind this back in a second, but if we want to know, we're given a prime. Okay, so now we can much more easily answer this question that we've been having. That is, if we have some odd prime and we're given a number A, and we want to know, is A a quadratic residue? We can simply make this calculation here and see whether it turns out to be 1 or not. If it doesn't turn out to be 1, then we answer no, it isn't. If it does turn out to be 1, we answer yes, it is. We don't have to square all of the numbers in ZP to see if we can find A. Okay, so this gives us a quick method for determining whether something is a quadratic residue. Okay, so this theorem, it gives a, so this theorem, what's important from our perspective here, this gives a polynomial time algorithm for determining if A is a quadratic residue. Okay, and what are we doing to determine if A is a quadratic residue? We are simply doing a modular exponentiation. Okay, we are doing this. We are going like this, a to the p minus 1 over 2, and we're asking, is it equal? Is it congruent to 1 mod p? That's our question. So in order to answer this question, is a quadratic residue, we do this. That is a Okay, a bit of a hiccup there with the video. So we're here. So what we've done is we've proved Euler's criterion, and what I'm saying now is that this gives us a polynomial time algorithm for determining if A is a quadratic residue, because that's the calculation that we need to make. We need to make the calculation A to the p minus 1 over 2. Okay, and we already spent a couple of videos back understanding how to do modular exponentiation quickly. So what we do here is we use our idea here is going to be to, it's a little bit bigger, use the square and multiply algorithm. Okay, so then we know that the time complexity of this is big O of log p cubed. Okay, so we have a way in polynomial time of determining if a number is a quadratic residue mod p odd prime. Okay, I think what I'll do actually, since we've introduced the idea of what is a quadratic residue. We've introduced the idea of what's a quadratic non-residue. We saw how to find it by brute force, and we've now also covered how to use Euler's criterion to determine whether a number is a quadratic residue or not. I think I'll stop this video here, and I'll start up with part 3, where I define the Legendre symbol and then talk about quadratic reciprocity. Thank you.